Hello everyone and welcome to our last lecture session in the scope of atoms, convolutional neural networks. This architecture which is maybe most responsible for the tremendous success of deep learning, at least in its earlier days. We haven't looked at it at all, and it is about time to make up for that, and this is exactly what we will do in this session. Um, we have 5 parts here in total. Following a brief introduction, I want to briefly talk about some of the applications of CNNs in the scope of image processing. That is just the environment in which CNNs have become so famous, dealing with image data, and we will introduce CNNs in that scope, which I believe is beneficial to understand what they do and why they work so well in this field. And once we understood why they work well in the scope of image processing, we can, in the last subchapter, CNNs for a non-image data, briefly revisit use cases of CNNs in other applications, specifically in the scope of natural language processing, which is just one of the other applications in which they gained a lot of popularity. In general, any type of data where there is a sequential structure, you can also use a CNN. We have introduced RNNs as the go-to approach for sequence data. Last session, when talking about the transformers, we have basically learned that there are other architectures which might not be or might not appear as suitable for sequence data. Conceptually RNNs are beautiful for sequence data. Practically, they suffer this limitation that you can't scale them very well, and this limits their applicability for big data settings where you really need to crunch through a lot of data and where you need to parallelize your computations to do that. That's the problem of RNNs. CNNs remedy that problem to a large degree and therefore can generally also be used when you have sequential data. But before going there, let's revisit what are images, how does the computer see images, and why is image data actually sequential data, or in which sense is image data sequential data. That's a part of the introduction, then some apps, and then the core part is the third chapter here, the inner mechanics, as I used to say, of the CNN when processing images. That's what's awaiting us, so let's get going. We have talked briefly about the ImageNet database and the annual ImageNet competitions that used to be organized, where people would try to perform a couple of image processing tasks using the images from this enormous database, ImageNet. And although this was not the only task in later challenges, image detection or object classification, classifying whether an object is part of an image or what object an image is actually showing. That was one of the tasks in ImageNet. That was the original task. Earlier challenges focused exclusively on that task. Later on, when the state of the field in computer vision developed, the ImageNet challenge involved more than this object classification task, but it's a very useful task for us to introduce CNNs. And if you try to detect an object in an image, you can understand that as a classification problem. You want to classify, for example, whether an image shows a human face or a cat or a dog or some other type of object, and that is classification. Or you can look at it as from the perspective of multi-class classification, when you say, I have a bunch of different objects. Let's say I have 100 different objects, cat, dog, human, banana, car, whatever. So I have 100 different categories, and I train a neural network in order to predict which of these objects is shown in an image. And then I feed my network with images and let it classify whether the image shows cat, dog, car, plane, whatever. Very much like a language model, where you're predicting a probability distribution over words. An object detection model can be a neural network that gives you a probability distribution over a finite, predefined set of object types. And what we see here is this bar chart depicting the progress that was made in years of the ImageNet competition, where the performance metric is classification error. This is why I was stressing that. Look at this challenge as a classification problem. You see the classification error, you see that error which human annotators achieve 5% error rate, and you see how this important, boundary, human performance, was basically taken by ResNet in the 2015 challenge, and later years further reduced the error. I think there was one competition in 2017, and since then, given that the state of the art has evolved and that image models became so powerful, they changed the rule of the competition so that this graph, I could continue it for one more year, but then nowadays I believe they do some sort of 3D object detection, which is yet more complicated and just does not compare to what was done before. And you also see here on the left hand side a picture of a neural network. This is ResNet, and while we don't need to go into too much detail here, two things are notable about this picture. Maybe you have recurrent blocks that you stack on top of each other, very much as in the transformer. In fact, the transformer was inspired by this image model which used blocks, each of which has a specific substructure in the block, and these blocks then repeat one another in a deep and typically a very deep architecture. So we have these blocks. Where's my pen? Well, they are color coded. What's the point in highlighting them? We have these blocks. You see how they reoccur: blue, yellowish, purplish, and greenish. And within these blocks, you see something like COF. That term here appears a lot. COF stands for convolutional layer, and we will look at what that is in the third part of the lecture. So, but even for now, we can conclude that a convolutional neural network is a neural network where we have a chain of convolutional blocks stacked on one after the other, or one on top of the other, thus giving us a deep network. That's already a good takeaway here from this picture without going into any detail. All right. So nowadays, any serious image model or model for computer vision tasks would use these convolutional layers. While they can be used in other applications, maybe as an alternative to an RNN or maybe as an alternative to a transformer, when we talk about images, you'll definitely want to use a CNN, at least as part of your architecture. Okay, some fundamentals. Maybe you have never used image data, or maybe you've never thought about image data. Let's talk about some fundamentals so that we can follow through later parts. How does a computer see an image? Very simple. It sees an image just as a matrix. At least for grayscale images, black and white as well, a computer perceives an image as a matrix, where we have two dimensions, width and height, and in each of these dimensions you have a bunch of individual pixels, small dots which are so close to each other that the human eye is unable to tell them apart. And this is how we see an image. Maybe this image of the close-up of the eye of this lady here. But if we would zoom in using some extremely powerful microscope and zoom in, making the image bigger and bigger and bigger and bigger and bigger, at some point we would see this little pixel matrix here, highlighted in the middle. That's essentially how computers store images, as these enormously big matrices of individual pixels, where one of these pixels has a certain color intensity. In the simplest case, in a black and white image, you have only two intensities, one black, the other white. And you could encode these either binary, 0 and 1, or, well, you could encode these binary, 0 or 1. Is the pixel white or black? That was the very early days of computer images. If we have a proper grayscale image, as we do see here, you need more than just black and white. You need different intensities, color intensities. How much white or how much black is there in the image? And a little bit of white and a little bit of black gives you some sort of grayish color. And commonly we encode colors using 1 byte, meaning that we have the number range 0 to 255. That is the range of numbers that you can encode with a single byte. Feel free to look that up on Wikipedia or elsewhere if you're a bit shaky with how computers store numbers. Color intensity is encoded as a number, and we use typically a byte to encode it. So we have 255 different intensities. And depending how much white and how much black you blend into one another, the darker the image is then depicted on the screen. So we have these shades of gray here. Haha. That is grayscale images. Of course, we like color images even better. That is not different. With color images, you also store it as a matrix on the computer, just that your matrix now encodes the multiple colors individually. It's not enough to just mix black or white. For color images that are depicted on the screen, you basically produce the color by mixing 3 base colors, red, green and blue, with different intensity. That's the RGB color system, red, green and blue. And depending on the color intensity of red and green and blue, respectively, you can produce all the beautiful different colors that you like. As we see here in this image, the same eye but colored, beautiful blue eyes this lady has got. And all we need is a bunch of pixels that are red and green and blue with different intensities. And then our human eye will see this nice image. Data structure wise, we now need the same matrix with dimension, number of pixels in the horizontal dimension times number of pixels in the vertical dimension. And each of these individual pixels has a value between 0 and 255, which encodes the intensity of the color red. And then we have a second matrix encoding the intensity of the color green per pixel for each of these pixels, and same for blue. Well, probably I'm talking a lot and too much, because the picture you see here is quite self-explanatory, I believe. So this is how computers store images. And that is just data. We could, for example, one way to process such an image using a neural network would be to construct an input vector where all we need to do we have this, well, in a grayscale image we have the single matrix, and a color image we have these 3 matrices, so we have a tensor. Tensor is a data structure where we have more than 2 dimensions, or if you have a matrix with additional dimensions, you call that a tensor. I'm not very formal today. And that data structure we would need to translate somehow into a vector, which is what we typically feed our neural networks. But that's pretty easy. We could just concatenate all the different rows in this matrix one after the other. Or similarly, we could just stack all the columns one after the other do that for each of the columns in the matrix encoding the red intensity, and then afterwards, once we are done, we stack all the columns of the matrix encoding the green and then the blue intensity. This operation, where we just stack all the columns after another or stack all the rows behind each other of a matrix, that operation is called flattening. So we can easily flatten our data structure here, our 3D tensor, into a long vector, which would have, if you flatten that whole thing, you would have basically width times height, pixels in the width times the pixels in the height, times 3. That would be the number of elements in your vector when you flatten it. And then you could feed into a neural network. And now, what's the issue with that? Has been done, by the way. That has been done, and it works, but it had issues. What are the issues? And the issue, well, basically you see it here. Scalability is the big bottleneck that you face and will not be able to overcome when you use a standard neural network, feed-forward neural network for image analysis. And I'm trying to illustrate that here. Let's say we have a color image. So we have these 3 color, well, I call these channels. This is how they're called, 3 color channels. That's what we saw before. For every pixel in the image, which has dimension x by y in my example, so we have x pixels in the horizontal dimension, we have y pixels in the vertical dimension, we have x by y pixels overall in the image, and for each of these pixels we need 3 different color channels, one for red, one for green, one for blue. So we have 3 by x by y pixels in total, which we could flatten into a single vector and then feed it through a neural network. The problem is that this neural network would have a very, very large number of weights, and because of that is infeasible to handle. And that might seem a bit bizarre given how powerful computers are, but we can actually look at a little example here. Let's say you have a photograph. You know, in ancient times, people were printing out photographs. Yeah, it's hard to believe, I know. They hadn't had smartphones or something like that, so they were actually printing out photographs. Bizarre thought if you think about it. But they did that, believe me. And then they were sticking that in books. It's ridiculous if you think about it nowadays. Sorry, feeling a bit, well, amused today. The weather is just too nice. Right, and a common format to print these photographs, 15 centimeters times 10 centimeters, 15 by 10. That was a common format to print photographs. Weddings or some special events. And the recommended resolution for a picture that you want to print in this format was actually 602 by 889 pixels. You can Google that. That is the recommended resolution. This is, let's say, the quality picture should have in order to allow high quality printing. Obviously, nowadays, if you look up the resolution of your smartphone camera, that's miles more than that. And with your smartphone camera, you could easily print out an A0 poster of an image in the highest possible quality. But we don't even need to go there, because even this relatively small image resolution, by today's standards, 600 by 900, let's say, or 602 by 889, that's very tiny image by today's standards. Pretty tiny. But it's more than enough to make the point. Let's say we flatten that image into a vector. So we have 602 by 889 pixels by 3 color channels per pixel. And well, 600 by 900, that's 54,000, and then by 3, if you work that out, sorry, that's 5, obviously that is 540,000. If you work that out, you'll end up with roughly 1.6 million elements in your input. And now revisit how neural networks work. Every feature in your input is fully connected to every unit in the hidden layer. Well, the hidden layer, that is up to you how big you make it, but normally if you have a very high feature, a very high dimension in your input, if you have a large number of features, you would also have a pretty sizable hidden layer. You would have a large number of hidden units in your hidden layer to avoid compressing the information too much when you feed it into the first hidden layer in your neural network. Make sure you fully understand that point here. If you have a tiny hidden layer, let's say you have 10 hidden units in the hidden layer, the output of that hidden layer is a vector with 10 numbers, right? Depending on your activation, these numbers might even be between +1 and -1. And you have 10 of these. If you use the 10H activation function, the output range of your hidden unit is +1 to -1. And if we have 10 hidden units, we have 10 numbers, +1 to -1 each. And if we now feed 1.6 million input units, feature values, 1.6 million distinct values, numbers with distinct values, we feed that to our neural network, and all that we get out of it is 10 numbers, each +1 to -1. How could it be possible to represent all the information in these 1.6 million feature values in just these 10 numbers? That wouldn't work too well. The hidden layer is a way to construct latent features that aggregate the information in the previous layer. And if the previous layer is large, you would not want to shrink the number of latent features too quickly. Let's say, for instance, we pick a hidden layer with 112 hidden units. Then our computational cost here is massive already. With this small image, we have a massive computational cost because for every input feature that is fully connected to every hidden unit, and we have 512 of these, in total we obtain roughly 8.3 to the power times 10 to the power of 8. That's 830 million weights, if I'm not misled. 830 million weights. Well, for simplicity, let's say that is a little less. It's more than a little, but it's almost 1 billion weights that we need to tune in just this layer, input to hidden. Almost 1 billion weights. Now note that Python typically uses 8 byte to store a float number. If you have 1 billion weights and you store these weights as a float, you use 8 bytes for each of these, so you have less than, but close to 8 billion bytes to store the weights connecting the input to the hidden layer. 8 billion bytes. That translates into 8 gigabytes. You need 8 gigabytes of memory just to store the weight matrix for the input to the hidden layer. We have powerful computers, but that's way too much. That doesn't scale. That can never scale. No, well, computers can advance no matter how fast they want. This is just a bottleneck that you are creating here. And again, that's actually not a very big image. Your smartphone takes images way larger than this one. You can easily work that out, right? How many megapixels does your camera have? Maybe 5 megapixels or something. So 5 megapixels. That's 5 million pixels. 5 million. Here, well, we just have 550 millions with this image resolution. So your smartphone will take 10 times of that. If it's an older smartphone, and if you have a new smartphone, the images that you take will be loads bigger than that. So it doesn't scale. We have a problem, we need a different solution. We need CNN. Okay, I think I made the point. Let's briefly go through some of the examples. Before going for the CNN, let's go through some of the examples, use cases that you address with CNNs. Or in former times where images were not so big, you would have addressed these use cases using feedforward neural networks, at least those that you could address. Like image classification, that's the most fundamental task, that's a basic task. It's also a standard task because it's so basic, classifying what an image is actually showing. You annotate images, airplane, automobile, bird, cat, deer, dog, frog, horse, ship, and truck. These are my classes. And for each of the class, I'm collecting a bunch of images. Remember, that is exactly what ImageNet is about. Classified images of various entities, many thousand different entities. And for each of these entities, you have thousands of images. Remember the thousands images of the banana I was showing in the previous lecture. All right? And we can use this database to train image models that are able to classify which type of object and image that we put in is showing. That's shown here at the picture where they illustrate the outputs with the highest probability that some image model, maybe that was ResNet, I don't know, could have been ResNet, or maybe it was some other popular image model, maybe it was VGT16, anyways, it was some image model. And you basically see how if you input a photo of a container vessel, in that case your image model gave the by far highest probability for the type or the output class container ship, and it gave a little probability for the class lifeboat and virtually zero for amphibian, fireboat, or drilling platform. And all the other many object categories, they are not shown here. The right hand side picture just depicts the top 5 categories, so all the others receive probability lower than that. And let's look at the second picture from the right in the lower row. We have this somewhat nasty picture of the dog behind the cherries, and the label of that image in the ImageNet database was actually cherry, which is a bit mean. This also tells you, should you have wondered, why would a human annotator not achieve 100% accuracy? Because there are images like that one where it's a little bit ambiguous how you classify that. This image here, that one here, right, that is annotated in the database as cherry, clearly it shows cherries, but the model predicted the class dog, or more specifically Dalmatian. Sorry if my pronunciation is wrong, I don't use that word very often. And grape is the second highest probability, or class with second highest probability, elderberry, bull terrier, or currant. So cherry does not even appear in the top 5 of that model. There we are. That's basically that's image classification. Hold on, I need to be careful here. It's not my native field. That is image classification. You have predefined categories and you classify your images. And it's important for applications such as image retrieval. Think about image search apps or websites where you key in some number and then you have the search query as your input, and now you need to classify whether an image matches that query. And well, to make that work, you can't do it on the fly. You must have tagged your image before. You need a computer program to tag your images, put them into different categories, maybe not mutually exclusive, but you need to have them classified somehow. And that is where image classification is immediately useful to do that. You could classify, maybe using the model we saw before. You put the images in your database through that model, and then you say, well, the 5 classes with the highest probability, according to my image model, I use these 5 classes to tag my image. So let me go back one step. If, let's say we look at the first image, if that one here is classified as mite with largest probability, black widow, cockroach, tick or starfish, then I could use all these 5 categories as tags for my image, maybe also storing the corresponding probability. And then if somebody keys in a search query for mite, I know immediately which images to depict. I depict, or I give as return to my user all the images that have been classified as mite with some probability by my image model. And I could sort these images in the order of the probability from my target class, mite, because I might have a bunch of models, I might have a bunch of images in my database where there was a classification of the class mite with some probability, but maybe a low probability. So I could use the actual probability for my search query for mite as sorting criterion. And this way I can build an image database and a retrieval, put a retrieval system on top of that. This is how I can build Google image search. And I would need a large database of images and a little bit of computing power on top of that, but this is basically how it works. Image retrieval. Now, object detection, I used to confuse image classification and object detection, or at some point I used the terms interchangeably, object detection and image classification, and I have to say that's wrong. It's not interchangeably, it's different task. Object detection is more complex, it's more difficult. It cannot be solved with classification alone, but you need classification as a building block. And that's shown here quite intuitively, I believe. Object detection means your task is more difficult than that just putting an image into a category. That's the mite, that's the container vessel, that's the cat, that's the dog. It means you want to identify what's actually shown in that image. And to achieve that, you need at least 2 steps, or you can decompose your task in 2 logical steps. One is to detect borders that delineate one object from other objects or just from the background. And you see these borders here. So the first logical task is to detect the borders of the object that an image is showing. And once you know these borders, these regions of attention or the regions of interest, as we say, once you have these, you can process every region of interest using an image classifier. That's the easier part. That is just image classification again. When detecting the regions of interest, you would also not know a priori how many there are, which is yet an additional complication. And earlier approaches toward object detection were really decomposing these tasks and had submodels for the detection of the region of interest or the regions of interest and a subsequent image classification model. State-of-the-art approaches can solve both these tasks in one go or using one model, but for us just to understand the task, it's important to make the point that image classification is a more basic task or problem than object detection, where we also, in addition to classification, need to know what are the objects, or where in the image do we see certain objects. And if you put it yet one step further, the applications also become more relevant. Semantic segmentation, and the picture reminds us that this is something, this enhanced object detection, this is something you need for autonomous driving. Where, well, what do I want you to take out of this picture? The thing is, if you imagine an autonomous vehicle, you have the image coming in from the different cameras and sensors showing the front road. What we really need for our autonomous vehicle is an overall understanding of the scene, of the road in front. For example, it's not so relevant to say, okay, so this here is a region of interest, and in that region of interest I see a car. And oh, by the way, here is another region of interest, and in that region of interest I also see a car. And here is another region of interest, and in that region of interest I see a pedestrian. Well, these objects have something in common. You do not want to drive toward them. I agree that if you drive toward one of them, it's worse to hit the pedestrian than hitting a parking car. Clearly that is worse, but ideally you don't want to hit any of these. In that regard, an overall and more abstract understanding of the scene is what you need, and that is semantic segmentation. And you see the color coding underneath, where the different colors sort of group similar objects to one another. And you see that the pedestrian, well, it was detected. Here we have the pedestrian being detected. But if that class is pedestrian, we also see that our system detected some more pedestrians that at least I cannot detect in that image. So it's not perfect, but we have an overall understanding of the scene, and this is what we want. All right, well, just some basic idea how you could realize such a system in a neural networking architecture. If you have an image and you put that through a neural network, the key point here is this funnel-like architecture, where you have first funnel, where the number of hidden units in your neural network gets smaller from layer by layer. We haven't had the lecture on autoencoders. The material is online if you want it, but we haven't really looked at that, and I said it's not part of the lecture. This funnel shape is very typical for what they call autoencoders. But I think you can, even without that lecture, make sense of that. We have features, we put that through a hidden layer. The hidden layer creates these latent features, and then we stack another hidden layer on top of that, where the features get transformed one more time, leading to new latent features, and we hope that the features get more and more abstract with from layer to layer, more high level, more generic. And this means that if we have this funnel shape of our layers, that they get smaller and smaller and smaller, we need to create latent features that are more and more abstract and able to capture, to summarize all this information. So we have a condensed, a compressed representation of all the data here in this part of the neural network. And from this compressed information, which really captures only the abstract insight, the high-level patterns of the input data, we basically make it, well, big again. We generalize these patterns in the second half of the filter to, in the end, obtain, as a result, another type of image. The output has the same shape as the input. That's noteworthy here. But what we see there, because we put the data through this bottleneck layer, is a compressed high-level summary of the original input. We do not have all the details. We just have a compressed view. We, for example, miss the fact that there are different types of trees in that image. That's not relevant anymore. We just want to know, okay, there are trees. We do not need to distinguish between one tree or the other. And this you can achieve with this bottleneck layers. Another application, image captioning. I mentioned that application several times before, where you feed in an image to a network and want that network to generate you a caption for that image. That is useful for, well, social networking sites where people would upload pictures and maybe they're too lazy to upload the pictures. As a provider of such a platform, you have all these pictures, some of which are not annotated. Maybe you want to offer some automatic annotation service. Maybe. That could be an application. And in these examples, you can see that some of the they are all automatically generated. Sometimes the model did a very good job. A white teddy bear sitting in the grass. Wonderful. That's a perfect description. I could not have done it any better. Or a man riding a wave on top of the surfboard. Full marks. That's brilliant. And in other examples, the, well, automatically generated description is somewhat getting into the right direction or is a bit off, right? A man in a baseball uniform throwing a ball. We of course see immediately that the man is not throwing but catching a ball, but apparently the corresponding deep neural network was not so adept when it comes to baseball. And in the last column we have some examples. A woman is holding a cat in her hand. Well, somewhat related, but not really on spot. Or we have a woman standing on a beach holding a surfboard. The last one is nice because that is a common pitfall. Sometimes the images, we have talked about the flattening, and sometimes you might, as part of the pre-processing, sometimes image get rotated. And of course the handstand is not a very natural position for a human being. So basically what the model probably has done, I'm speculating here, but probably what the model has done, it has tried to annotate the picture after rotating it. And if you rotate this picture, you have a human. The model believes that it's a woman. I would not be able to tell, but anyways, you would have a human basically holding up the hands, and then there is something on top of the hands. And then this area here that resembles water. And right here we have some water. That's probably how the detection was generated. Reminds us of the pitfalls. Also here some ideas how you do that. Actually, that's surprisingly straightforward. I mean, well, take that with a grain of salt, straightforward. But yeah, it's from an architectural point of view, it is not so complicated. You have your image and you feed that through an image classifier. Or even better, so here you have classification, but now that we are a bit more advanced, you could say, well, actually you want to feed that image through an object detection model. That's a bit more powerful than a classifier. And then might tell you that there are multiple objects in that image, like a cat and a skateboard. But, well, for simplicity here, we had image classifier, and then the output of that image model you feed into a recurrent neural network, where the image model basically initializes, that's the core part, it initializes the first hidden state in your neural network. And then this information for the initialization of the first hidden state, together with our token here, start, triggers the recurrent neural network that certainly was trained earlier on to output some text. Where since the input token is start, the first token that the recurrent neural network is generating will depend very much on the initial hidden state that is driven by the output of the image model. And then this information from the image model that came into the first hidden state, of course, is preserved and will also affect the hidden state at the next step. That is how RNNs work. But there, in addition, we have the previous output of the RNN as additional input. So we have an input straw, and we use that input straw and the previous hidden state to update our hidden state, and might then output something like head. That is how image captioning works. It's often a combo between a CNN and an RNN. And if you look at it from that perspective, that reminds us very much of the sequence-to-sequence architecture. Noting that, you could now say, I have an idea, let's replace the RNN with a fancy transformer. Obviously, you can do that. Well, unfortunately, I need to tell you, you would not be the very first person on the planet to have that idea and to put it into practice. All right, these are common application of image models. That slide I left blank for a reason. What about business applications? I would love to have a chat with you. Is there anything we can really make use of in econ and in management and in business? Question mark. If we do a little bit of brainstorming together, we could come up with some points, for sure. I'm counting on your creativity here, but still, I would argue that image models and image processing is a bit less prevalent in our target domain of management, of business administration and economics than structural data, time series data, and also text data. But clearly it plays a role and will maybe play an even bigger role in the future. Still, nowadays, fields like manufacturing, engineering also might be even more interested in image processing models. I want to focus on the CNN in the reminder, and therefore this just informs us about the standard tasks that will pop up when you read about papers, when you read papers on CNNs. Probably these applications that we've seen, object detection, image classification, will be the use cases in which people introduce their deep networks. So I wanted you to have some understanding. And feel free to post some suggestions, what we should put on that slide here on our Moodle page, and then I can, populate the slide a little bit, and we can sort of mimic the brainstorming which at this point would have come in the lecture, had it been a traditional lecture. Let's rather look at the CNN.